In this session, we learn second application of Gauss law. Say here we want to find electric field intensity due to an infinite sheet of charge. That means I write a figure like this. Say I write the heading first, electric field intensity due to an infinite sheet of charge. Infinite sheet of charge. Infinite sheet of charge. Say we imagine an infinite sheet of charge like this. Say even though we write it looks like finite, but we can imagine it is extended in all sides to the infinity. Now we imagine this is having positive charges on it. That means continuous distribution of positive charge with the charge density sigma, that is surface charge density sigma is there. Now we want to calculate electric field at point P at some distance r from it. So for this we take the electric field intensity is always normal to this sheet because it is an infinite sheet of charge and only the contribution from straight part of the say sheet of charge which is in straight line with the point P is only to be considered. Therefore we take like that and we imagine the electric field intensity is normal here like this. Now what is the Gaussian surface for this? Say we can imagine a right circular cylinder piercing through this sheet or a rectangular box. Say I take a rectangular box like this, say. This is the Gaussian surface what I can think of. On this side also it comes out. On this side it comes out. On this side it comes out. Like this. Say this one. And on this side also electric field intensity is there because it's a simple sheet, so field exists on both sides. Now this is the Gaussian surface what I have written with green color there. And this area we take it as small area ds. This side also it is ds. Now what is the total electric say flux through the Gaussian surface, this rectangular box? In fact, it has only two small areas, ds and ds, on both sides of the sheet. So, what I write is total flux phi equals E into ds plus E into ds. I cannot take a whole lot of the things because there is no need to consider it is an infinite sheet of charge, only two surfaces, ds and ds to be taken, and that too electric field intensity is same there. Therefore, E ds plus E ds, that is 2E into ds is phi. But according to Gauss law now, what is the charge enclosed inside this, say on the sheet of charge like this, it looks like this, say. On this area, charge enclosed can be written in terms of sigma. Sigma, the surface charge density, can be written as, say, Q by area. Here it is Q by ds. Therefore, Q equals sigma ds. If I substitute that here, phi equals, say, 1 by epsilon naught charge according to Gauss law. Say, phi equals 1 by epsilon naught, charge is sigma ds. We substitute for phi also. 2E ds equals 1 by epsilon naught sigma ds. If you cancel ds there, E equals sigma by 2 epsilon naught. Sigma by 2 epsilon naught is the expression for electric field intensity due to an infinite sheet of charge. This type of questions may be asked for 3 marks in the board exam as the application of Gauss law. Let me go through the derivation once again. Electric field intensity due to an infinite sheet of charge. Say, how do you imagine the infinite sheet of charge? Just imagine it is made up of only positive charges like this. So you can see the positive charge from this side or this side. That's why we have written electric field on both sides. So once we have taken infinite sheet of charge with charge density sigma, we can choose a point P at a distance r. And now we can think of the electric field intensity due to this infinite sheet of charge is always normal to that sheet. So at P I can write the electric field intensity like this, which is normal to that sheet. Now with this idea we can imagine a Gaussian surface. Say here I took a shoe box like that is rectangular box, parallelepiped or cuboid you can think of. That cuboid, one face area is ds, other face area is ds, and this cuboid is piercing the sheet. That is half of that this way, half of that on the other side of the sheet as I have written there. Now say one end of that includes the point P there where electric field intensity is E. Now the total flux through this Gaussian surface, a rectangular box, is only through these areas ds and ds, not through the side surfaces, because all the electric field lines are perpendicular to the sheet of charge. Therefore, net flux through this Gaussian surface is E into ds plus E into ds, because one EDS is this way, one EDS is this way, EDS plus EDS. Why we summed them? Even though electric fields are opposite, because we are thinking of total electric flux coming out of the Gaussian surface. Therefore, this way also flux is coming, this way also flux is coming out of the Gaussian surface. So I added them EDS plus EDS, which gives us 2 EDS. Now, say we calculate what is the charge inside this Gaussian surface. For that I take charge density sigma as q by area, q by ds, but q equals sigma ds. Therefore, phi equals 1 by not charge according to the Gaussian surface, but for charge I substitute sigma ds, and for phi I substitute 2e ds. We get E equals sigma by 2 epsilon naught. This is the formula for charge, say electric field at any point near to the infinite sheet of charge, sigma by 2 epsilon naught. With this, we go for the third application and the last application of Gauss law, that is electric field due to a spherical charged conductor. Electric field due to a spherical charged conductor. So for that, we consider a sphere like this. Say, I write electric field due to a spherical charged conductor. Spherical charged conductor. Say for that I consider a hollow sphere of radius r like this. Hollow sphere means nothing inside, only surface is there. We imagine this surface is charged positively. As it is a sheet of conductor, the charge is uniformly distributed. We take this as the center O, and I imagine a point P at a distance r from the center, and let r be the radius of the sphere. Now, electric field lines are always perpendicular to the conductor. Here for this spherical conductor also it is perpendicular. Therefore, electric field intensity at P can be taken to be normal to the conductor. So it is along this direction. In fact, in this case, electric field intensity is radial, that is along the radius, which we know radius is always normal to the conductor. Therefore, electric field intensity is always normal to this conducting sphere. Therefore, what is the choice for Gaussian sphere now? Say, it is another concentric imaginary sphere, including point P on its surface. Let me write that. Say, we take a concentric Gaussian sphere, concentric sphere as Gaussian sphere, like this, which has same center O. Now we imagine a small portion ds there, small portion ds, whose area vector is this way, ds vector. Area magnitude is ds and area vector is outward normal. it is ds vector here. E vector this way and ds vector this way. Observe. Now, electric field intensity vector and ds vector both are in same direction. That means there is no question of cos theta, because theta is 0, cos 0 is 1 in calculating the flux. So, flux through this small area ds is E into ds only. But we imagine whole surface, Gaussian surface, is divided into small such areas throughout the sphere. Remember, it is a three-dimensional figure, but we have written it on two-dimensional. That's why it seems to be a circle. But many students, when they write the answer, they say this is a circle, but it is not a circle. You always say it is a sphere. This Gaussian sphere, when we take the total area of that, we have to take the spherical area. Therefore, total flux through this whole Gaussian surface, flux phi equals sigma E ds. Now, but we have to calculate what is E and what is ds. Say, as for all the points on the Gaussian surface lies at same distance from the center, at all points on the Gaussian surface, electric field intensity should be same. That's what we call a spherical symmetry. We can write like this: by spherical symmetry, E is same at all points. Please remember to write this point exclusively when you write it in the exam. Therefore, if I take E as same, then E can be taken out of the summation. Phi equals E into sigma ds. But what is ds now? ds, sigma ds is total surface area of the sphere. I write sigma ds is surface area of Gaussian sphere. That is imaginary sphere, what we have imagined, what I have written in green there. Gaussian sphere. It is, surface area of the sphere is 4 pi r square. 4 pi, say small r to be written, because r, small r is the radius of the Gaussian sphere. 4 pi r square. So, that is sigma ds. Now, we apply the Gauss law by applying the flux and all those things. Say we know flux equals 1 by epsilon naught charge. So, flux is E into 4 pi r square, which is equal to 1 by epsilon naught. I write Q itself, because whole lot of this charge on the sphere is inside the Gaussian sphere. Whole sphere is inside. Therefore, 4 pi r square, E into 4 pi r square equals 1 by epsilon naught Q. Therefore, E equals 1 by 4 pi epsilon naught. On cross multiplication, we can write Q by r square. E equals 1 by 4 naught Q by r square. Can you identify which is this formula? We got very similar formula for electric field due to a point charge. Observe, in this case, when a point P outside the charge conducting sphere is there, you can apply the same formula what you apply for electric field intensity due to a point charge. That means when you take a point outside the charge conducting sphere, the whole sphere acts like a point charge at the center of the sphere. That's why the same expression comes. You may remember one thing. You learnt very similar idea without any derivation in the first year chapter, that is gravitation chapter, where we took the whole lot of mass is actually at the center, and it creates the gravitation everywhere. So, if you want, you can remember that. Now, recollect it from the first year book. Chapter number 8, gravitation. With this, what we derived now is the electric field intensity for any point outside the charge conducting sphere. So, we can take this as case 1, where we learnt electric field intensity outside the charge conducting sphere. Now, we think of what happens when the point P inside the conducting sphere. Inside the conducting sphere. Say, we imagine, we write the figure once again. say this is our charged conducting sphere with charge on the surface of conductor. This is center. I consider point P now inside at a distance r. So we write the Gaussian sphere now as a concentric sphere again. Observe, in case of conductors, the charges always reside on the outer surface, what we prove later on in the next chapter also. But for the time being, you imagine the charges on a conductor always reside on the outer surface, no charge inside. In this case, say the Gaussian surface is this green one what I have written, including point P on its surface. But the flux through this to be calculated, we write flux phi equals EDS sigma. But observe, there is no flux because no charges are present, no flux inside, and no Gaussian, actually no charge inside. We can straight away take Gaussian's say law. We write case 2 here. Gaussian law, that is phi equals 1 by epsilon times charge. But observe, charge is 0 inside the conductor, therefore 1 by epsilon into 0, which is equal to 0. That is flux equals 0, which implies E is also 0. E is also 0. That means electric field intensity at any point inside the conductor is 0. You may know very famous Faraday's cage experiment. I will tell you one thing now. I may share one of the videos there. I will just tell you, this is a remarkable result. Say, we usually say, our elders usually say, when it is raining with lightning and thunder, you must not go outside in the open field. Why? Because in the open field, if you are the taller one, nothing else is there, then lightning strike may strike you. Therefore, to avoid that, you must not go out. This was the elder saying. But if you are in a car or an enclosed vehicle, even when lightning strikes to your vehicle, you are safeguarded. Why? Because of this fact. If a car is made up of conductors, so you are inside, just like the point P in this example or in this application. So no electric field is inside the conductor. You are safeguarded even though lightning strike happens to your vehicle. And this was first proved by Faraday himself by a famous and dangerous experiment, what is called as Faraday's cage experiment. I share a video for this. Just go through that video. It's a beautiful video which shows you how we are protected as there is no field inside the conductor. So this is the second case. And the third case is also there. What is the electric field intensity on the surface of conductor? We don't prove that. We simply take case 3. Electric field intensity on surface of conductor is maximum and it is equal to 1 by 4 pi epsilon q by r square, where r is radius of the conducting sphere, as we said. But in the exam, if they ask you to prove electric field intensity due to a spherical charge conductor, you take only case 1 and case 2. Case 1 is a point outside the conductor. Case 2 is point inside the conductor. Case 3 is not required. That may be required for solving the numericals. But now, with all these things, can we think of writing a graph of variation of electric field intensity due to a spherical charge conductor with respect to the distance? Observe, we have two situations. I write that situation now. Say, we think of that like this. Say we have electric field inside as 1 by 4 pi epsilon naught q by r square. Electric field outside, this is outside, and electric field inside is 0 for all points. Electric field on surface is 1 by 4 pi epsilon naught q by r square. With this idea, we can write a graph of variation of electric field intensity versus distance from the center. I take this as distance, this as electric field intensity. Now observe at this point, say this is R, the radius of the sphere, and all the points outside this are R greater than R. For all the points inside, this is the sphere inside. We imagine a physical situation there. Say this, there I end this. This is the center of the sphere. Up to this only, the R is there. Up to this only, R is there. And this region becomes outside the sphere, this region becomes outside the sphere, only this is inside. Observe now, for inside, for all points inside, that is inside, it is 0. So no field there. And on this dotted line, it is on the surface, it is maximum. Therefore, we start from this point. It is maximum there. And for all points outside, it is inversely proportional to square of the distance. Therefore, the curve will be like this. The curve will be like this. Observe the graph for electric field intensity variation with respect to distance from the center of a charge conducting sphere is like this. You need not write both sides. In the exam, you can write only one side thing. If you are asked, this is, say, if E and this is D, then you write D equals R there, then you can simply write the graph like this. Only one part of the curve. No other part is required. You can write sphere also there on top. Even though if you are not written, nothing to worry. Only the graph to be written like this, a curve. So this concludes our chapter 1, that is electric charges and field. In the next chapter, we learn about the potential. Before that, in the next session, I take up some numericals in this electrostatics regarding Gauss law and other things.